Welcome to today's afternoon session. We will have in this session Supratik Chakraborty, who will tell us about the knowledge compilation for synthesis.
Thanks, Raina, and thanks everybody for coming for this session. So I'm going to talk about primarily the synthesis problem and the role of knowledge compilation in that. I'm going to define these terms, and we'll also see that quantification is an essential step in that process. So as a byproduct, we get knowledge compilation for quantification. Okay, so here is a toy synthesis problem. Let's say I'm trying to design a memoryless arbiter. Yesterday, Rainer talked about an arbiter with temporal logic specification. So let's say this is just memoryless. So at every point it receives, at every time instant, it receives one of three requests. Let's say these are Boolean variables, and it has to give one of three grants. And the properties that we want are, of course, we want mutual exclusion. So no two grants must be asserted at the same time. We would like the arbiter to be responsive, which means that if somebody has requested, it should not deny the grant to everybody. At least somebody should be granted. And I think it's reasonable to expect that the arbiter should grant only if it is asked, which means that if it is granted to user 1, then user 1 had requested, and it is granted to user 2, and user 2 had requested, and so on. And all of this is just at every time point it receives these, and it's supposed to generate G1, G2, G3, which satisfies this. So there is no memory in it. There is no temporal aspect of it. So our job is now to synthesize G1, G2, G3 as Boolean functions of R1, R2, R3, such that these specifications, these formulas are always satisfied. Now note that these formulas actually do not tell us what is G1 in terms of R1, R2, R3, or what is G2 in terms of R1, R2, R3. They just tell us some relation between the requests and the grants. So that's why such specifications are also called relational specifications. But the synthesis task is to derive functions out of these specifications such that the specifications are satisfied. So of course, one can look at these specifications for some time and come up with simple solutions. For example, one might say that, okay, if request 1 is there, I'm going to grant 1. And if request 1 is not there, but request 2 is there, I'm going to grant 2. And if neither request 1 nor request 2 are there, but request 3 is there, I'm going to grant 3, which would be kind of prioritizing between the three users. And sure, that is one way of synthesizing the functions, but it turns out that the space of solutions, which means the space of functions that one can write in terms of R1, R2, R3, which satisfy these specifications, is actually quite diverse and rich. And here I'm just going to show you some of them which are completely different from each other. So here is the first one that I said, that if request 1 comes, grant 1, otherwise there's no request 1, but request 2, grant 2, and similarly for grant 3. Here is another solution, looks very different from the previous one. In fact, there's no permutation of the indices of the first solution, which will give you the second solution. But you see that, grant 3 has a similar kind of behavior, but these have very different behavior. And here is a third solution, which is different from the first two again. And no permutation of indices will give you the third from the first two. And here you see that this solution looks somewhat like this. This also looks somewhat like this, but both of them are present. And this looks somewhat like this, coming from a different solution. So there is a rich space of things. And of course, if one permutes the indices, one can always multiply each solution by 6. So the question is that existing synthesis tools which can solve these kinds of problems, they will take a specification like this, and they will output one of these solutions, which the tool thinks is the best for you. I mean, you don't have any further control over it. I mean, Raina talked about yesterday about soft constraints and hard constraints, but really even among the solution space for soft constraints and hard constraints, there can be a very rich diversity. And so if you have a tool which just takes the specification and outputs something, one actually doesn't get to see this, this entire space of solutions and perhaps use further optimization criteria to choose among them. Okay, so if I were to abstract this problem, what we had was a vector of Boolean variables, which I'll call as inputs, which were the requests. And there was a vector of Boolean output variables, which were the grants. And then I had a formula phi, which was the relational specification. And I was trying to synthesize functions for each of these outputs such that for every input, when I replace the outputs with these functions, the specification evaluates to true. This is at an abstract level what I was trying to do. And this is all good as long as we know that for every x, there is some value for y which will make phi true. Then one can indeed ask, give me at least one such set of y for every x. But what happens if there are some x's for which no y's are going to work to make the specification true? So it is not the case that for every x, there exists a y such that the specification evaluates to true. And such kinds of specifications are also called unrealizable. Raina mentioned about this yesterday. And we want to ask, is synthesis still meaningful for such specifications? In the literature, actually, these specifications are kind of wished away mostly. But of course, yesterday we heard that one can talk about the best one can do about such specifications. So I'm going to argue that there are actually fairly interesting problems, synthesis problems, whose specifications look like this. I mean, it's not the case that for every x one can find a y, but whenever one can find, it's very interesting to find those. Okay, so as long as there is some x for which I can find a y, I think this problem is.
Second bullet point, is that a for all y theta? Is that a for all x for all y? Or is that actually an exist x for all y?
This one?
Yeah. Is that actually supposed to be for all y exists, for all x exists y?
Yeah, it's for, so it is not the case that for every x there exists a y, which means that there are some x for which there exists no y.
Got it.
Right. And here is a very nice example of this, which is, let's say my input is a 2n-bit unsigned integer, and I have two outputs, each of which are n-bit unsigned integers. And here's my specification. So I have written it here with some abuse of notation, but I hope all of us understand, and it certainly can be written using a Boolean formula of size O of n squared. So I want to say x, which is the input, is going to be the product of the outputs, integer multiplication. And none of the output should represent the number 1 in n bits. These are unsigned integers. Right? So if you stare at this specification for a second, you'll realize what I'm asking is a non-trivial factorization of a 2n-bit integer. Okay, so this is my specification, and indeed, even if I do the simplest way of representing multiplication as high school multiplication algorithm, this can be represented by a Boolean formula of size at most O of n squared. And now, if I ask you that synthesize the outputs as functions of the inputs, I'm basically asking you for a factorization circuit. Okay, and note that I've specified the n over here, so it could very well be the case that these functions for a certain value of n look something, and for another value of n maybe they look different. So this is really asking for a non-uniform circuit family for factorization. And this immediately tells us that the synthesis problem in general is going to be hard, because I can write the specification compactly, but then we don't even know, it's open whether we can do factorization, even in the non-uniform setting in polynomial. Prime numbers, yeah. But that doesn't give me,
like if n is 2, I could give it the input 7, and it'd be impossible to meet the specification.
oh yes, yes, absolutely. So that's where I'm coming to, saying that this is in the classical sense not a realizable specification, because there are some inputs for which there won't be any outputs.
Yeah.
And yet this is an interesting synthesis problem, because
It's interesting, for sure. Yeah.
because whenever I give you a number which is not a prime, I would like to get non-trivial factors.
Oh, good. So that's another condition. You allow it to fail.
Yeah.
If there is no, okay.
Exactly. So if there is, if for a given x there is no y which will work, then actually any y is as good or as bad, because everything is going to fail. But for those x's for which there exists a y, I would like to get the right y. And interestingly, following up on your question, that yeah, so for non-prime x we get non-trivial factors. And if I am able to actually synthesize these functions, I can just plug it inside this and I get a primality check, right? So so even specifications which are not realizable in the classical sense, which means for some inputs there are no outputs which are going to work, the synthesis problem for them is still interesting, because I think this is certainly one important example. So this sort of leads to this problem, which is called Boolean functional synthesis, where we're trying to design a system which has some Boolean inputs, some Boolean outputs, and there's a relational specification. And our goal is to synthesize the outputs as functions of the inputs, such that it satisfies the specification whenever possible. And this can be formally written as that for every x, as long as there is a y which satisfies this, I would like the synthesized functions to satisfy this. And of course, if there is no y, then whatever function I put here, both of them will evaluate to false. So such functions are also called Skolem functions in the literature for y in terms of x in the formula phi. And so we're basically doing Boolean Skolem function synthesis here. So this is the problem statement. This is what we want to do. We want to synthesize these Skolem functions. So this problem has a storied history. Of course, Skolem functions occupy a very important position in first order logic, where we are basically trading off quantifiers for function symbols. And the seminal work by Thorab Skolem in 1920s and Jake Herbrand from 1930s. However, the treatment here is more on the existence of these functions and to use these functions to prove very powerful results, but not on how to synthesize these functions. Given a formula, how do I get the Skolem function? And we know that there's a Skolem function, it has certain properties, preserves satisfiability once you substitute and all of that. We can trace even further back, and George Boole and later Lowenham, they had considered this problem of Boolean unification, which is taking two Boolean formulas and trying to substitute Boolean terms for Boolean functions for variables over there, such that the two formulas become equivalent. And I mean, Boolean unification has connections to the problem that we're talking about, Skolem function synthesis. So interestingly, this problem was looked at even before Skolem was around to do Skolem function synthesis, to talk about Skolem functions. Okay, I just showed some simple examples. There turns out that there are a lot of other applications. This is certainly not an exhaustive list, nor is the set of citations exhaustive. This is useful in repair of circuits and program synthesis, certifying QBF SAT solvers, disjunctive decomposition of transition systems, so a whole bunch of other things. And of course, people have worked on this, and there are several approaches that have been used. So in recent times, for realizable specifications, when you know that for all x there exists y, phi of xy is true, one can look at the proof of that and extract scaling functions out of it. There is something related to iterated function composition, which doesn't scale very much. It blows up very fast. There is BDD based, and I'm going to talk about it briefly, because that's kind of one of the knowledge compiled forms from which you can do efficient synthesis. I'm going to focus more on this, which is trying to come up with a new normal form for Boolean functions, which allow efficient synthesis. And then there are other techniques like incremental determinization, input-output separation, guess, check, and repair. All of these are for synthesizing the function, synthesizing one set of functions from the given specification. As I said, the focus of this talk is slightly different because we not only want to synthesize a function, but we want to have a form where all the functions can be synthesized efficiently. The entire space of functions is kind of easily accessible and can be synthesized. So, so that's where we are. So, the immediate question that comes to mind is that how hard is it going to be? And of course, from the factorization example, we know that it's not going to be easy. But the answer to this question is quite nuanced in the sense that it depends on how you represent phi and how you represent the scaling functions. And we will see that there are very interesting connections about how you can change the representation of phi to make this problem simpler, or for other representations, it might become harder. Okay, so let's look at the most relaxed representation, which means I'm not putting any constraints on how you want to represent. So these are just Boolean circuits. So phi is a Boolean circuit, and let's say my scaling functions, I'm also okay having them as Boolean circuits, no other property required of those. It's not very hard to see that this ought to be NP hard. It's interesting that actually, not very surprising again, that even if you allow exponential time, you can't avoid large sized scaling functions. So there are problem instances where even if you went and tried to solve this problem using exponential time, the smallest scaling function that you can synthesize is still going to be large.
What is the this is your problem that's NP hard? What is it? Is the size? What
yeah, so you can think of this. So here, these y's are the outputs and x's are the inputs, right? So suppose I didn't have any inputs and I had only outputs. So in that case, I'm asking, can you give me constant functions which will make the specification true? Right. So a very special case of this would solve the decision problem. Yeah, so so it turns out that under these complexity theoretic assumptions that the polynomial hierarchy doesn't collapse, we will always have specifications where the smallest scaling function will be superpolynomial, and if non-uniform exponential time hypothesis fails, the non-uniform is because we are allowing the circuits to change as we go from one end to another end, then the worst case scaling function. These are not surprising, but that's what we know if we have the most relaxed representation. So it's unlikely that we'll have efficient algorithms over here. So let's look at the other end of the spectrum, and let's say I have a very constrained representation, and Randy Brandt talked about BDDs, and other speakers have also talked about BDDs. So if we use BDDs, and actually even a more constrained kind of BDDs called input first BDDs, input first ROBDDs, which means that all the input variables X are ordered before the output variables Y. They can be ordered between themselves in whatever way, but all the input variables must appear before the output variables. So this is an example of a BDD representing such a specification. then it turns out that, and if you want the outputs also as ROBDDs, so this is kind of constraining how the input specification is going to be represented, and also how the output functions are going to be represented. So if this is your setting, then it turns out that you can do it in polynomial time, and it's actually very simple to see how you can do it. So I'm going to illustrate right here on this example. So in this example, these are the inputs, the x's are the inputs and the y's are the outputs, and the solid edges are the true edges, the dashed edges are the false edges. And so what you can see is that, and I know that all the inputs appear before all the outputs. So I go to the first node, I look at this level where the outputs are first starting to appear. And at this node, I ask, is there a path to the one leaf? And if there is a path to the one leaf, it means that I can set the outputs to values, in this case, 1 and 1, which will make the specification true, right? So whenever I have this input, I can set the outputs to 1 and 1 to make it true. Whenever I reach here, which could be either like this or like this, I can set the outputs to y2 is 0, y1 is 1, or y2 is 1, y1 is 0, and I'll satisfy the output. I'll satisfy the specification. And here, I guess, if I set both of these to 0, I'll satisfy, right? So if I give you this BDD, it's kind of trivial to come up with constants at each of these nodes. And then this now gives, from here, you can construct a BDD for y2 and for y1, because now basically you have a decision diagram, which is probably not reduced, but then you can apply the usual BDD, the usual way to reduce the BDD nodes from non-BDD structures. And this will immediately give you BDDs for both y2 and y1. And once again, you can see here that there are multiple ways in which you could have satisfied the specification. At this point, you could have chosen y2 is 0, y1 is 1, or vice versa. And so BDD actually exposes this whole thing. I mean, once I give you the representation as a BDD, it's out there, what the different Skolem functions can be and how you want to get them. So the question we want to ask is that, but of course, BDDs have their own problems. We know that they're very order dependent on the variables. They can blow up. So we ask that, do we really need input first ROBDDs to have polynomial time synthesis? And the answer to that is no. And in fact, I'm going to talk about a much weaker form than ROBDD, exponentially more succinct than ROBDDs, which we call synthesis negation normal form. And this is going to yield polytime algorithms for synthesis, as long as the Skolem functions are represented as Boolean circuits. And remember, here in this case, the Skolem functions were also represented as ROBDDs. But here, as long as we are fine with the Skolem functions as Boolean circuits, I can do with exponentially more succinct representations of the specification. And yeah, maybe this picture will come to later. This is like really saying that, I mean, I showed you how from a BDD you can get the Skolem functions. This is really showing how from a d-DNNF specification you can, put some m copies of these if there are m outputs, and then you can get the Skolem functions. But we'll get to this later. Okay, so we've already seen that from input first ROBDDs, if I want the Skolem function, so this is the representation of the specification, and this is the representation of the Skolem function. From input first ROBDDs, if I want the Skolem functions to be synthesized as ROBDDs, I can do in polynomial time. If I have NNF circuits, and if I want this, if I have a NNF circuit representing the specification, and I want the Skolem function as NNF circuits, so these dotted lines means these are conditional exponential bounds. There are complexity theoretic conjectures, as I showed earlier. So this is kind of the map that we have, which says that the complexity of synthesis really depends on what is this representation for the specification and representation for the Skolem function that you're choosing, right? So for example, from ROBDDs to NNF, I can do polynomial. But from ROBDDs to ROBDDs, I mean, the best we know is exponential, and we don't have a better bound over there. But from input first ROBDD, we can get to NNF circuits in polynomial, and also to ROBDDs in polynomial. And of course, here, the Skolem functions, they're just, I mean, they only have the inputs in them, right? The Skolem functions are expressed only in terms of the inputs. So an ROBDD is the same as input first ROBDDs. In the specification, you have inputs and outputs. The Skolem functions, you have only inputs. So this is the kind of map that we have. And of course, if one looks at other representations which have been talked about over the last few days, like decomposable negation normal form, then disjoint, what is that D for? Deterministic, yeah. Deterministic decomposable negation normal form, and other kinds of things. So these can all be located in this map. I've just shown here a small sampling of it. And this also kind of motivates the study of the d-DNNF and its cousins. And that's what we're going to do now. Okay. So to begin with, I'll present a very simplified view of synthesis, and I guess this will drive what are the features, what are the properties that we need in this form that we want to use for synthesis. So suppose I had a one output specification. So this just had one output and whatever, some bunch of inputs. And let's say this big rectangle here denotes the set of all possible assignments to X, to the inputs. So I can divide this space into 4 parts, depending on whether phi of x1 is true or false, and phi of x0 is true or false. Okay. And once I do this division, I guess it's not hard to see that in this quadrant, every Skolem function must evaluate to true, because if I put 0 here, the specification is falsified. And similarly, in this quadrant, every Skolem function must evaluate to 0, because if I put 1 here, the specification is falsified. But in these two colored quadrants, here, no matter what the Skolem function evaluates to, the specification is satisfied. Here, no matter what it evaluates to, the specification is falsified. So we are free to choose what f1x should evaluate to in these two quadrants. But in these two things, every Skolem function must evaluate to 0, and every Skolem function must evaluate to. So this shows that, although there is a diversity of Skolem functions, like I showed in my first slide, there are some common properties among them. There are some inputs on which all of them must agree. And then there is some room to play around over here. And so, if I ask, so what is f1x? So there are many possibilities. I could just say phi x1. I guess that would amount to choosing this to be 1 and this to be 0. So whenever phi x1 is true, f1x is true. I could have negation phi x0, which is probably choosing this to be 0, so that whenever phi x0 is true, it evaluates to false. And similarly, I could have many other things. And interestingly, this picture also tells us that the number of choices is exactly the number of ways in which you can assign values to the function over here. So the number of satisfying assignments of phi x1 is equivalent to phi x0. So these are the two things. Number of satisfying assignments, 2 raised to that. So even for a single Skolem function, the number of choices can be pretty large. Okay, so one output synthesis was easy. So for multi-output synthesis, we are just going to try to reduce it to one output synthesis. So we will first construct a new specification, which is, for the time being, let's say we are somehow doing this quantification. We'll see how to do this quantification. So we have quantified out all the output variables other than 1, and that gives us a new specification. And what's this telling you? This is specifying a relation between x and ym such that whenever you satisfy the specification, you know that there is a way to assign values to the other outputs, which will satisfy the overall specification. So that is nice, because now I have just a single output specification, and I know if I can synthesize this output correctly, there is always a way to synthesize the other outputs. So, we just synthesize for ym, we synthesize the Skolem function. And then what we do is we then go and try to construct a new specification from this, where we have quantified out all but the last two. And so this now has ym minus 1 and ym in it. But remember, I have already found the Skolem function for ym. So I can just treat this as ym minus 1 is the only output, x and ym are the inputs. I can get the Skolem function in terms of x and ym. And because I have already found out ym in terms of x, I can substitute it and get the Skolem function for ym minus 1. And I can keep repeatedly doing this. So this looks like a simple strategy to sort of address multiple outputs. There are a few important things here. One is that there is an ordering on the outputs, and I'm first trying to synthesize a one output thing for ym and then ym minus 1. So it looks like I have already implicitly ordered the outputs. And there is this existential quantification that's happening here, which is we have to figure out how to do that. And in fact, this sort of shows the connection between synthesis and existential quantification, which is kind of elucidated over here, that if I can do efficient computation of this quantifier elimination problem, right? Here I'm not, so this is not a SAT problem, because I'm not eliminating all the variables and coming up with a true or false answer, 0 or 1 answer. So I'm eliminating part of them, and I'm eliminating them in a sequence. But if I can do efficient computation of this from what I just said in the previous slide, it should be possible for us to efficiently compute the Skolem functions. And note the other way around is kind of trivial, because if I can compute the Skolem functions, I can just substitute the Skolem functions and achieve existential quantification. So this is a very strong connection between the two. If I can have a representation that enables efficient quantification, then the representation will also enable efficient synthesis. And therefore, this motivates us to ask that what would be such representations which will enable efficient quantification. But remember, we don't want to quantify things some arbitrary subset of variables. I mean, we are saying that there's an order and we want to quantify it in that order. So as long as that is enabled, as long as that is doable efficiently, in terms of the representation size, we are doing fine. But remember the lower bounds that we talked about. So even if we find such a representation, we know that compiling to this representation will be inefficient in the worst case, right? Because there are at least conditional lower bounds. So therefore, trying to find a representation for efficient synthesis is kind of equivalent to trying to find a representation for efficient quantification, and vice versa. So this now motivates this thing about, given a specification, how do I compile it to a form from which I can do efficient quantification and hence efficient synthesis. So this is the Wikipedia definition of knowledge compilation. So it's a family of approaches for addressing the intractability of a number of artificial intelligence problems. This is what Wikipedia says. And a propositional model is compiled in an offline phase to a form that supports subsequent queries in polynomial time. So so it looks something like this. For example, you can have a formula, which could be a CNF formula or a circuit, and a compiler might compile it down to a BDD or a d-DNNF. And then in polynomial in the size of this, you can do lots of other things, which otherwise are hard. So of course, this compilation can be worst case exponential. We cannot avoid it given the complexity of these problems. So in our context, we would like the knowledge compilation for synthesis to be once again given a specification, which could be CNF formula or a circuit. And then I also need to know what are the inputs and what are the outputs. Just the formula is not good enough. And then I want to get some compiled form here, which we call the synthesis negation normal form. such that I can then synthesize colon functions. I can do a sequence of quantifications, quantifier eliminations in polynomial time in the size of this. Okay, so this is the knowledge compilation problem for synthesis. Okay, so let's see what's the problem if I try to do existential quantification with normal circuits. These are the most compact things that one can think about. No restrictions on the circuits. I mean, negation normal form, every circuit can be converted to negation normal form. Linear blow up, every AND OR circuit. So here is my specification phi x y, and at the leaves here I have shown these are the output variables y1 negation y1 yn negation yn, and these are the inputs. And if I were to do usual existential quantification, so I will basically, suppose I'm trying to quantify out the variable y1, I will set y1 to 1, right? Which means I will set these leaves to 1 and those leaves to 0. And then I'll set y1 to 0, so setting these leaves to 0 and these leaves to 1. And then I would like to OR them up. So that's the definition of existential quantification. Problem with this is that there's a potential doubling of size that's happening for each variable that I'm quantifying. So therefore, we would like to see if we can start off with such NNF representations and convert them to some other form, which can probably allow us to avoid this doubling of size. So what is this new form that, well, it's not a new form, it's just a transformation, an existential quantification friendly representation. So what we do is we take the NNF circuit as a DAG. Let's say it's like this. All the negations are at the leaves. The inner nodes are only ANDs and ORs. And then we look at all the leaves which have the outputs negated, and we introduce new variables over there, which I call them overline or bar variables. So earlier I had negation y1, negation y2. Now I have y1 bar and y2 bar. And note that if I look at the function represented by this root, this function when I had negation y1, negation y2 is semantically different from the function when I replace these by y1 bar, y2 bar, obviously because I've introduced new variables and I've gotten rid of some of the literals that I had earlier. So this we call the positive form of the specification, and I can do it for every output literal, every negative output literal. And you can see that this is doable very efficiently. You can just replace the literals, have new variables over there. So why are we talking about this? Because these circuits have certain interesting properties that, first of all, for example, they're monotone with respect to all the yi's and yi bars, right? Because it's NNF, so there are no negations inside. And I've just removed the negations from here. And we're going to use this monotonicity in what I'm going to show just now. So this was our picture earlier that we had an NNF circuit where I was setting the variable to 1 and 0. And now what I'm going to do is I'm going to take this positive form where instead of y1 and negation y1, there is y1 and y bar. And here I was setting them to 1, 0 and 0, 1. And here I'm going to set them both to 1, 1. And because this circuit is monotone, I know that this, whatever function was represented here must imply this, and similarly whatever function was represented here must imply this. Follows from the monotonicity of the circuit here. And therefore, if I OR them up, that implication will also hold. And so this looks like a very cheap way to get an over approximation of the existentially quantified formula. The question is, we would like this to be equivalent. So what is the other thing that we need over here such that the implication holds in the other direction as well? Because if it does, then we can effectively replace this quantification by this. Okay. So let's see. I mean, we know that this exists. Y1 phi xy was already implying this phi hat with y1 set to 1 and y1 bar set to 1. We want to know when does this other direction hold. So let's see. We can ask when does the other direction not hold, and from there we'll get a condition of when it holds. So if this does not hold, it means this side has to be true and that side has to be false, right? That's the only way that an implication does not hold. So we must have this phi hat with y1 and y1 bar set to true as true, and exists y1 phi as false. But exists y1 phi, if I just expand it out in its definition, it is phi with y1 set to 1 or phi with y1 set to 0. This has to be false. But then I also know that phi with y1 set to 1 is the same as phi hat with y1 is set to 1 and y1 bar is set to 0. Remember, in phi hat, the negation y1s were replaced by y1 bar. So phi with y1 set to 1 is the same as phi hat with y1 set to 1 and y1 bar set to 0. So if I want this or this to be 0, then each of them individually has to be 0, which means that phi hat with y1 and y1 bar set to 1, 0 must be 0, and phi hat with these set to 0, 1 must be 0. And because phi hat is monotone, it also means that phi hat with y1 and y1 bar both set to 0 must be 0. Okay. So now if you look at this, when y1 is 1, y1 bar is 1, this function evaluates to true. When y1 is 1, y1 bar is 0, the function evaluates to false. 0, 1, it evaluates to false, and 0, 0, it evaluates to false. So what does it look like? It looks like the AND function. So it's basically, this implication does not hold exactly when these conditions are satisfied, but this is exactly the same as saying, can phi hat realize y1 and y1 bar? Which means, can I set values to the other variables in phi hat, except the y1 and y1 bar, such that phi hat becomes equivalent to y1 and y1 bar. So the insight that we gain from here is that if phi hat cannot realize this, which is what we also call the AND unrealizability, then we know that this implication must hold, and this implication in any case holds, then these two would be semantically equivalent, right? So this basically tells us that if I want to do quantification efficiently without a blow up, remember phi hat is linear in the size of phi. So if I want to do quantification without a blow up in the size, without a doubling in the size, then if I can ensure that phi hat cannot realize y1 and y1 bar, then I can effectively do that, right? So what does it mean? I mean, how do I know whether phi hat can realize y1 and y1 bar? Like, I mean, we had some circuit for phi hat over here, right? How do I know whether this realizes y1 and y1 bar? So this turns out to be a SAT call, basically an unsat check. So we are asking that phi hat with both of them set to 1 is true, and phi hat with 1, 0 is false, and 0, 1 is false. So is this whole thing satisfiable? If this whole thing is satisfiable, then it can realize y1 and y1 bar. If it is unsatisfiable, it cannot realize that. And this was for one variable, and I can now do this inductively for the other variables because I'm quantifying them in sequence, right? So if this holds for this variable, then I can get the result of quantifying out y1 by just doing the substitution. And in that, I can again check whether y2 and y2 bar is AND unrealizable. Then I can get the result of quantifying out y2 and so on. Okay. So basically, this looks like is a very crucial property that whatever representation we have, if I just at the leaves replace the negation y's by y bars, then I should not be able to realize these ANDs. So then, we can go and ask that what are the normal forms in the literature that enforce this AND unrealizability? And it turns out that quite a few of them already enforce AND unrealizability. So this is the decomposable negation normal form from Adnan Darwish and Pierre Marquet. So they, what they say is that the circuit should be such that you can't have paths from two different paths from the same literal to an AND gate, or paths from a literal and its negation to an AND gate. So this is actually much more than what we need. All we needed is we should not have y and y bar, I mean, they also disallow this, but anyway, this is a sufficient condition, right? So if a circuit is in, if the specification is already in decomposable negation normal form, it already satisfies the and unrealizability condition. So then this is good. So this is sufficient time for polynomial time and space synthesis. We can weaken this by saying that, well, all I require is that the y and the y bar should not meet up at an AND gate. There should be no topological paths from y and y bar meeting up at an AND gate. And this is also sufficient because this also ensures and unrealizability. And we can then generalize it even further by saying that let's look at the circuit, and maybe it's okay to have such AND gates inside the circuit, but at the root, can I realize yk and yk bar for every yk in the ordering of the outputs, right? So this is basically saying that can I order the outputs, and then for each output, can I ask whether I can realize yk and yk bar over there when I assign some kinds of values over here, and then one can work out the conditions, and then it suffices to assign only once here and allow all possible assignments here, right? So we have a linear ordering of the outputs, and then in this linear ordering, we just keep asking this question that, is there an assignment here such that when you set all ones here, can this become yk and yk bar? If it can, then it's violating the and unrealizability condition. If it cannot, it satisfies the and unrealizability condition. And if this works for all of the outputs, then we say that it's in synthesis negation normal form. And this also turns out to be a sufficient condition. And interestingly, this condition is far weaker than the condition that, for example, a BDD ensures this, a DNNF ensures this. But this condition turns out to be far weaker, so much so that we can get exponential gaps in the representation size. So, so here is an example of SYN-NNF. So here is a formula written down as an NNF circuit, and then and this representation is neither in DNNF nor in WDNNF, because you have things like y2 and negation y2 going and meeting up at an AND gate. So this doesn't satisfy any of the forms that were there in the literature earlier. But now if I can take the same circuit and say that, okay, here is my ordering of outputs, and then I'm first going to ask that, can I make this root behave like y1 and y1 bar, but there is no y1 bar here. So there is no way of making it behave like y1 and y1 bar. So we are doing okay for y1. But once I'm doing okay for y1, when I go to check for y2, I'm allowed to set y1 to 1 and then ask, can I make this look like y2 and y2 bar? And now once again, there is no way to make it y2 and y2 bar. Although there in the original circuit, there was a path from y2 and negation y2. But because of this simplification, it's now, there's no way to make it y2 and y2 bar. So this representation isn't SYN-NNF with respect to this ordering. But then if you flip the ordering, then it is not, because I have to ask, can I make this behave like y2 and y2 bar? And indeed, there is a way of assigning values to the other variables that makes it behave like y2 and y2. So, so the same representation may be in SYN-NNF with respect to one ordering of outputs and not in SYN-NNF with respect to another ordering of outputs. And so this definition is order dependent. One can also come up with an order independent variant saying for all ordering of the outputs it should be, but then that becomes much stronger. And here is kind of the succinctness map for where SYN-NNF is with respect to the other things. I'm not sure if the colors here are showing up properly. So we have an unconditional exponential succinctness of SYN-NNF with respect to ROBDD, doesn't depend on any complexity theoretic conjectures. And the other two, which is the exponential succinctness with respect to deterministic decomposable negation normal form, is conditioned on P not equal to VNP. and w-DNNF and the weak DNNF and SYNNF is conditioned on p not equal to np. And of course, this was already shown earlier that DNNF is unconditionally exponentially more succinct than ROBDD. So what you see looking at this picture is that this form we have just seen suffices for quantification in a given order, and therefore it suffices for synthesis, and it can be actually exponentially more succinct than several of the other forms, which also satisfy this and unrealizability condition, but can be much larger. And here is how we finally use this. So suppose I have given you a specification in SYNNF, and then the outputs are represented as y1 bar, y2 bar, and then there is a particular way of fixing values to these outputs and stringing them together that actually gives you the Skolem functions for y1 and y2. So this is effectively, we are doing existential quantification by setting both of these to 1. Because it's in SYNNF, this achieves existential quantification, and then we are setting. And remember, there was a lot of possibilities for choosing a one output Skolem function, and we are basically choosing these one output Skolem functions here. So we can show that if this circuit, if this representation had size m, then all the Skolem functions can be represented by a circuit of size m times that, with at most order m squared additional connections. So if I have this in SYNNF, I can actually do synthesis in polynomial time, starting from the SYNNF representation. But of course, converting an arbitrary specification to SYNNF will incur worst case exponential given the lower bounds, conditional lower bounds. Okay, so given this, we actually have two algorithms for compiling from actually arbitrary circuits to, could be CNF, could be arbitrary circuits to SYNNF. So the first algorithm, C2SYN, takes the input as CNF, and then it generates a SYNNF out of it. And this is really some optimizations on top of the D4 tool, where decomposition into components with disjoint support is done, and we branch only when and unrealizability fails. And this is another tool that we have called deconflict, which can take an arbitrary Boolean circuit as input, convert it to SYNNF, and it uses counterexample guided transformation to enforce and unrealizability. And this turns out to be more powerful than this. C2SYN builds on top of D4, which actually compiles to d-DNNF, deterministic recomposable negation normal form. And because we know that that's a much stronger form than what SYNNF really requires, so it's not surprising that deconflict achieves better performance. So this is some results on benchmarks. Maybe at this point, so I also had some slides on, or maybe I'll just very quickly go through this, that we have all seen sufficient conditions for polynomial time synthesis. Can we also get necessary conditions? And it turns out that it is possible to do this. So I will not go into the technicalities of it, but it is a further generalizing the forbidden semantics of SYNNF, saying that can we divide the outputs into groups and then linearly order the groups? Earlier we had the outputs were linearly ordered. Now the outputs are divided into groups, and they're sort of partitioned into groups. The outputs are the leaves, and then they're linearly ordered. And then after that, it is pretty much the same similar condition like what we had for DNNF, for SYNNF. And this turns out to be both a sufficient and necessary condition, which means that which means that of course every specification in this format can be compiled, can be transformed to Skolem functions in polynomial time, but every representation form which allows, like for example BDDs or SYNNF or whatever d-DNNF, every representation form which allows compilation in polynomial time, which allows synthesis in polynomial time, can also be compiled to this form in polynomial time. So therefore, this is, just polynomial time away from any other representation class which allows efficient synthesis. So in that sense, it's also a necessary condition. So, and of course, this also enjoys some nice properties. So I'll just skip those in the interest of time. And then there is a sort of simple way of transforming a class C of efficiently synthesizable specifications to this form by actually synthesizing. I mean, this is of course just an existential proof. This should not be the actual compilation algorithm, by saying that if it is efficiently synthesizable, I can synthesize it, and then I can use the Skolem functions to transform it into this form. Okay. And then I guess we also have a compiler for compiling to this, more general, necessary, and sufficient form. But that compiler is much less efficient. So, to conclude, we've talked about some new normal forms for efficient Boolean functional synthesis. This allows quite efficient compilation. This is not so efficient, but this is a sufficient condition for polynomial time synthesis. This also gives a necessary condition. And as future work, I mean, we have heard the last few days, even today, a lot about certification. So how to certify these compilation algorithms is interesting. And as I said right at the beginning, that these compilation algorithms are not just giving you one Skolem function from a specification, they're making available the entire space of Skolem functions, all of which can now be efficiently synthesized. And of course, this fine-tuning and all these are of course always to be done. And then can we go beyond the Boolean case? Can we do first order specifications in first order logic, some restricted theories in first order logic? And can we use similar representation forms to do efficient synthesis? So that I'll end. Yeah, there are questions. Yeah, Nikolai.
I might have 5 questions. I'll take one of them more. So, sure. So you said, Bond, so something less than first order is just finite domains?
Something less than?
Less than first order would be finite domains. The y range is not over 0,
right.
1, but
right.
0, 1, 2, 3.
Right.
Does your representation lend itself to a finite domain version with a y and y hats?
Yeah. So of course the naive answer is one could encode it as Boolean, but of course that doesn't work. So even if you go from the Boolean to the finite domain, the synthesizing one output itself is not as easy. Here I could just synthesize it. I mean, we basically said I can very efficiently synthesize one output, and then I can reduce the multi-output case to the one output case. But if I say that this one output can take on, let's say, whatever, 1,000 values, I don't have such simple forms for coming up with the Skolem function from that one output. So particularly, I mean, for example, if I take a bit vector, right? So wide bit vector.
Okay. So
and then if I'm talking about a permutation, right? I take an input bit vector and it gives some properties of a permutation, which gives me an output bit vector. Finding out that permutation is not easy, even for a single output.
Good, thanks. Just one question then. You're tied to 2QBF, not d-QBF. So yes. Your Skolem function is always a function of all x.
Correct.
All the y's depends on all the x's, as opposed to d-QBF, sum of the x's.
Yes.
And does your knowledge representation depend intimately on the 2QBF, or does it work? Can you make it work for
the DQBF thing? Can we make it
can
work?
you make it work for 2 DQBF? Or is it fundamentally tied
2
to
DQBF? What would that mean?
is the knowledge representation, is that fundamentally tied to that all the Y's depend on all the X's, or are you able to
Have
relax the
dependent
restriction?
sets.
Yeah.
Yeah, so this one is tied to the 2 QBF. Every output can depend on all the inputs. So we have been doing some work on not trying to come up with a representation for DQBF, but I think there has been work. Basically, you can take a DQBF specification and you can extract some specifications on only the dependent sets. And then you can probably try to apply this and then try to lift it. But it's not a direct representation. So, I mean, you can solve a DQBF problem by projecting onto the dependent sets and then correcting them later on. I mean, DQBF is a much harder problem, right? Let's be complete. So this representation does not work for DQBF. I mean, it does not directly give you.
Well, I mean, you have a heavy hammer, so the question is really how heavy is the hammer? How hard is it take? But thanks for this.
Yeah, so I mean, we tried, but we failed. Maybe there is a way to do knowledge compilation for DQBF as well. We tried using this, but we could not. There was no obvious way to do this.
A question that's probably similar to the one just asked. Are there any natural synthesis problems that involve more than 2 alternations of quantifiers? For all X, there exists Y. For all Z, there exists W. Because some of these methods may not work if the output, you would like to do the first block and then pass it to the next.
Yeah, of course.
Are there any such natural synthesis problems that you hear these alternations?
Yeah, I mean, turn-based games and all.
Turn-based games, yes.
Yeah.
So how, do you handle them iteratively, or is it another method for those?
So it's still QBF. It's not DQBF,
Yes.
but you have a linear ordering among the dependencies, right? Every existential variable can depend on all the universal variables to the left
Yes.
of it. So it turns out that this can be adapted to that setting.
Without worrying about how your output looks in terms of the input? I mean,
No, we have, I mean, it's not directly applicable, but this can be used to solve. Basically, what we're saying is that there's a linear ordering among the dependent sets, right? And so at least one very simple way to do it would be to treat all the existential variables to the left of, right? So you have, let's say, exists for all exists. If I treat the first block of for all exists also as for all, right? Because we are allowing unrealizable things. So it's perfectly possible that for some of those valuations, there is, right? So there exists X for all Y exists Z. And if I treat it as for all X for all Y exists Z, then I can express Z in terms of X and Y. And it's okay that for some of these X's, there may not be any Z, right? But then I can substitute that and then reduce. So this would be, you know, the very base level algorithm. And then there are certain optimizations you can do on top of it.
There are no more questions. I guess we can thank Supratik again.
Okay.